Okay, and here's our favourite thing, is to have a nice genetics question where there's lots of marks to be picked up from doing genetics crosses and simple substitution calculations. I mean, honestly, to get a genetics question, you're just absolutely laughing. So, we're going to follow the rules. In fruit flies, the allele for grey body, big G, dominant to the allele for ebony body, little g. And the allele for normal wings, big N, dominant to the allele for vestigial wings, little n. Vestigial winged flies heterozygous for grey body. So we've got grey body, vestigial wings, and they're heterozygous. Grey body, big G, heterozygous, big G, little g. Vestigial wing flies, little n, can't be anything else. We're crossed with ebony bodied flies, so ebony body, little g, heterozygous for normal wings, big N, little n. So, remember, in a genotype, parental genotype, 2 alleles per characteristic. In a gamete genotype, we've got that separation of chromosomes, there's 1 allele. So we need to FOIL. So we've got genotype here, FOIL your genotypes. So first, big G, little n. Outside, big G, little n, got one, don't need another. I'm going to put a circle around my gametes so I know that they're separated out nicely. Inside, little g, little n. Last, little g, little n, got one, don't need another. I'm going to put my cross in there so that I don't get muddled. Big G, no, little g, big N first. Outside, little g, little n. Different. Little g, big N, got one. Little g, little n, got one. So, and then they've left me a lovely space to do my Punnett square in. So parent 1, big G, little n, little g, little n, little g, big N, little g, little n. And here they've left me space to write my offspring genotypes. So big G, big N, little n. I'm going to do them one at a time so I don't get in a muddle. And so that is going to be grey, normal. And I need to match it down. I'm going to put a semicolon there, separate it out. I've done that one. Little g, big N, little n. So that will be ebony body, little g, ebony, and normal wing length. Take that one off, I've done that. Big G, little n, little n. Not got that already, have I? No. Okay, so that's a different one. Big G is grey. I'm just going to keep checking up here because you know, you really need to make sure that you don't make a really daft mistake. And little n, we're calling that vestigial, which I can't spell. Vestigial. And I need to make sure that my spelling is right because I've been given the spelling. So I've done that. Little g, little n, little n. So that's going to be little g, little n. So little g, ebony. And my little n, vestigial. So 4 lines, 1 mark each. That means you've got to have all 4 genotypes matched to the phenotypes. Okay, so the numbers of offspring from several such crosses were grey normal, 241. So this would be a 1:1:1 ratio, wouldn't it? 1 to 1 to 1 to 1. So we've got all those types, 241, 220, 272, 267 and 1,000 offspring altogether. Okay? Oh, here we go. The chi-squared test can be used to find out whether they fit that ratio. Give a suitable null hypothesis for the investigation. So remember, null means no difference. So there is no difference between the observed ratio and the 1 to 1 to 1 to 1 ratio expected. Okay, complete the table to calculate chi-squared. So expected, we've got a 1 to 1 to 1 to 1 ratio, that means a quarter of my 1,000. So if I divide that by 4, and I can do that without recourse to a calculator. So, observed minus expected, minus 9, might need my calculator in a minute, minus 30, we've got 22 more there, and 17 more there, and I need to square them then. Now what is important is that you remember that squaring in that, you're going to have plus signs only. So 9 squared I know, because I know my 9 times table is 81. 30 squared, 30 times 30, 900. 22 times 22, 484. And 17 times 17, 289. Now normally, if I was in an exam, I'd do those 4 sums again. Just because I don't want to make a mistake. We then need to divide by expected, so 81 divided by 250 is 0.324. Observed minus expected all squared, 900 divided by 250 is 3.6. Put 2 O's after that. Decimal places, keep them to the same thing. 484 divided by 250, 1.936, and lastly 289 divided by 250, 1.156. And again, you know, in an exam, just check that, check it again, so you know you've not made a pig up. And then I need to add them all together. 1.936 plus 3.6 plus 0.324. So that gives me a value, chi-squared value, 7.016. And I don't think anybody would be too distressed if you'd rounded that to get 7.02. Explain how you would find out. Oh, so they're not going to make me do it, they just wanted me to explain how I'd do it. How I'd find out whether the value obtained for chi-squared makes me accept or reject the null. So what do you, so they just want you, you just need to walk through that process that you would carry out. So, I would use the P equals 0.05 column, and so I'm imagining my little chi-squared table. It's got my p-values across the top, it's got my degrees of freedom down there, and I need to isolate a critical value. So, and how many degrees of freedom? And 3 degrees of freedom. Remember, it's the number of phenotypes, 1, 2, 3, 4, minus 1 degrees of freedom to identify the critical value. So, What would I do with that number then? I'd look to see if it was bigger or smaller. If my calculated value was bigger than the critical value, I would reject the null hypothesis. And if it was lower, I would accept the null hypothesis. And I need to put in both of those things. I would accept the null acceptance, the hypothesis. Because it said it should be accepted or rejected, so I need to talk about both of those things. Okay, so the allele for vestigial wings probably arose as a mutation of the allele for normal wings. What is a gene mutation? Again, this is just, this is really straightforward. Have you learnt this stuff? So, gene mutation is a change, I know I say don't use the word it. I would, in fact, in an exam I would write a gene mutation is, but, life's too short when you're videoing. It is a change in the base sequence of the DNA. Okay, super duper.